So last time I went over the general idea and the basic structure of one of the input ports. So now let's get a little bit more specific, starting with power supply ranges and input ranges. I figure being able to measure plus or minus 10 volts at the input and plus or minus 50 milliamps will be good enough for anything that I need to do. My bench supply has a plus or minus 12 volt power supply, which would be good for my instrumentation amplifiers. That should give me enough range to measure my plus or minus 10 volts. And also I have a plus 5 volt supply, which I can use for driving the relays and maybe the Arduino. The Arduino's analog inputs take a range of 0 to 5 volts, so I'm going to have to design all of the amplifiers and circuitry in there to take that voltage and current range and convert it to a voltage between 0 and 5 volts. My current measurement should look like this. I got some tenth of an ohm resistors to use as sense resistors, so my plus and minus 50 milliamp range would turn into a plus and minus 5 millivolt range across this resistor. So if I give my amplifier a gain of 1000, then that will amplify it up to a range of minus 5 to plus 5 volts. And then at the output of that, I can put a resistor voltage divider with one end tied to the 5 volt power supply. And that has the effect of compressing the voltage range by a factor of 2, and also giving it a DC offset of 2.5 volts. So that makes it perfect for going into the Arduino's analog inputs. And the voltage divider might not seem like such a great idea because it compresses the voltage range and basically reduces the gain. It's just too convenient of a way to add the DC offset that I need, so I'm going to use that. And then for my voltage measurement, that's going to look similar, except I actually want my amplifier to attenuate. I want it to have a gain of 1/2. So it'll compress my input voltage range of plus or minus 10 volts down to plus or minus 5 volts. And then the same resistor voltage divider will compress that again by a factor of 2 and then shift it up so that it can be used by the Arduino. Having a gain of 1/2 gets kind of interesting, and I'll talk about that in a bit. But even though it's not amplifying, I still want to use the instrumentation amplifier circuit just so that I can get the high input impedance and the common mode rejection so that I can make floating voltage measurements. And now let's get a little bit more specific with some resistor values. So here's the instrumentation amplifier as I'll be using it to make current measurements. So I'll have my sense resistor across here and some current flowing through there, and I'll be measuring that voltage across it. The front end I want to have a gain of about 1000, so 47K and 100 ohms will be close enough. They'll sort of get me in the ballpark. In the back end I want to have a gain of 1, so it really doesn't matter what these resistors are as long as they're matched to each other. So I'll just throw some 10K resistors in there because whatever. And now's the part where I have to deal with some unpleasant realities. The resistors that I have are all the cheap 5% tolerance resistors. So none of these resistors are going to be exactly what I expect them to be. So for one, this could throw off the gain, but I'm not really worried about that. Even by design, the gain is not going to be exactly 1000. And the reason I don't really care about that is because as long as it gets me sort of in the ballpark of 1000, I can just calibrate out the rest in software. But what I can't calibrate out in software is a bad common mode rejection ratio. So I'm going to have to add some knobs to manually tune the common mode rejection of the in-amp. So what's important to remember with the back end is that it's not actually important that R2 here be matched to R2 and R3 matched to R3. The only thing that's actually important for common mode rejection is that the ratio on the top is matched to the ratio on the bottom. So what I can do for the back end is add a single potentiometer on one side of it, and that will let me adjust this ratio to match this ratio, whatever those end up being. And then the question is, how much will I have to add to one of these two resistors in the worst case to end up balancing those ratios again? So now to make an estimate of that, let's say I have 10K resistors. That could be off by 5%, and I have 4 of them that could be off by 5%, so it gives me 2 kilo ohms that I'll need to adjust one of the resistors in the worst case. So I can throw a 2 kilo ohm potentiometer in there, and that should allow me to adjust the ratio of the bottom to match the top, even in the worst case scenario with these crappy resistors. Now on the front end, matching these two resistors is actually more important because this is where all of my gain is. And it also gets a little bit more tricky because when I add a potentiometer to here, I can only add resistance to one of these two resistors, which means I'm going to need to design one of these to be larger than the other and then adjust the amount of resistance that I add to the smaller one. So if I pick 47K to be my small resistor, I have a couple of options for the large resistor. I could have a 51K resistor or a 56K resistor. Those are the the next two standard sizes for 5% resistors. So now let's assume that the 47K resistor is as large as it could possibly be. So I have 47K times 1.05, so it's 5% too large. It could be up to about 49.4 kilo ohms. If I make the other resistor a 51 kilo ohm resistor, and let's say that's 5% too small in the worst case, I could actually end up with a 51K resistor that's smaller than the 47K resistor. So I'm going to have to take the large resistor up another step. Let's say 56K times 0.95 in the worst case. And that gets me above the worst case large 47K resistor. So what that means is that I can use a 56K resistor and a 47K resistor, and even if they're the worst possible values, I can still correct it by adding onto the 47K resistor. Now let's take the other worst case scenario where the 47K ohm resistor is too small and the 56K is too big. So let's say we have 56K which is too big by 5%. And let's see what the difference is between that and the 47K resistor, which is too small. So the worst case scenario difference between the two resistors is about 14 kilo ohms. So what that means is that if we're making one of these resistors 47 kilo ohms, we should probably make the other one at least 56 kilo ohms, and then put a potentiometer here that we can adjust that is, let's say, 20K. So the fact that we're using 56K makes sure that it will always, and even in the worst case, be larger than the 47K resistor, and the having 20K for the potentiometer makes sure that even in the worst case we'll be able to add enough to match this resistor to this resistor. Another problem that I could have comes from the high input impedance of these amplifiers. So let's say, for instance, that I'm measuring the current for a circuit that's otherwise not connected to the in-amp circuit. The common mode voltage could be floating, and then the common mode would change with any electrical fields in the air or the phases of Saturn or whatever. I could fix that by adding a very weak connection to ground on either end with some very large resistors. And that way, if the circuit is otherwise not connected, this would give it an electrical connection to my circuit that would keep its common mode voltage at ground. Now, I don't want to put these resistors on because, first of all, that would reduce the input impedance of this circuit to whatever this resistor value is. And then also, any imbalance in these two resistors could degrade common mode rejection. So I'm going to leave these off for now, but I'll leave room to add them later if I need to. And then I'll only put them on if I have problems with it. And then for the voltage measurement, things get a little bit interesting. It's impossible to give the front end a gain of less than 1. But if you take R1 down to 0, or RG up to infinity, or in this case both, it just turns into 2 voltage followers. So you have a gain of 1 at the front end. And the back end is where I'll actually do the gain of 1/2. And I can do that with a 4.7K and a 10K resistor. And again, a 2K potentiometer is good enough to adjust the common mode for the back end. And even though they won't actually do anything at all, I still want to add a couple of resistors here, just so that I have the option to add a resistor in the middle to give this thing some gain if I ever want it to in the future. So let's say I put a 10K in there, that's good enough. I also have some 15K resistors. I can put one on the other side, and then potentiometer in there, and 10K potentiometer should be enough to adjust the common mode in that case by the same math that I used up above. And again, I might need some resistors on the inputs to make sure that the inputs aren't floating. It's also a good idea to make sure that the gain that I want is actually reasonable, because remember, with negative feedback we can only lower the gain of an op-amp. So the largest gain that I want is 1000, and that's going to be split between the 2 op-amps in the input stage of the in-amp. So 500 is the highest gain that I'm going to have. So here are the data sheets for the op-amps that I'm planning on using. If we find the voltage gain, we see that's going to be at least 25 volts per millivolt, or at least 25,000. So we're lowering the gain by well over an order of magnitude, which should be just fine. So the next thing to deal with is the relays. The relays need 5 volts to switch, and the Arduino's outputs only put out 3.3 volts. Also, the relays take a lot of current to switch, and the Arduino's digital outputs might not be up to the task of supplying that much current. But the Arduino can drive a transistor just fine, and a transistor can handle the current of the relay. So that leaves another problem of what happens when this transistor turns back off again. So this relay coil is a big inductor, and it wants to keep pushing all the current through it, which can build up a big voltage and then break the transistor. And the standard thing to do in that case is to put a diode across the relay coils, so that normally when the relay is turned on, the diode is reverse biased, so all the current goes through that coil. But then when the transistor shuts off, all the current that is still flowing through that relay coil has a place to go, until eventually all the energy that was stored in the magnetic field turns into heat, either in the diode or in the resistance of the coil. The 2N3904 and the 2N Quad 2 are pretty standard small NPN transistors that you can use for this sort of thing. Either one will work, but the 3904 is a little bit cheaper and can only draw about 200 milliamps through it. But that's more than enough for my relay, so that's what I'm going to be using. And the last thing I want to worry about is the default positions of these relays, because the relays are stuck in one of the positions when the relay is powered off. And I don't want to plug something into my input port while the whole thing is turned off and accidentally short something out. So I want these two relays to default to this extra path here and away from this buffer and ground. And then also I want this relay here to default to open. That way these two input terminals are connected to the fewest things when the whole thing is turned off. And the one thing I haven't talked about is this buffer, which is just going to be a voltage follower, so that's not really too important. And in the next video I'm going to start putting this all together.